All right, guys, so in 7.2, we're going to expand a little bit on some of the stuff that we talked about in 7.1. We're going to focus mainly on spanning trees as well as MSTs being minimum spanning trees. Max STs are similar. You just look for a maximum rather than a minimum. So let's get started. So with spanning trees, in the case of a network with a positive redundancy, going to be trees within the network that connect its vertices. These are the spanning trees of the network. Let's talk a little bit more about redundancy. So redundancy, what we mean by that is that there are extra edges that we don't need. So redundancy basically means that we have extra edges that are not needed. And so really when we calculate the redundancy, we're looking at how many extra edges are there. Now, an easy way to do that is to figure out what a minimum number of edges would be, and then to see how many there actually are. Now there is a formula, so if you wanted to just plug everything in, you could use this formula right here. But let's just think about it. If our network has n equals 8 vertices, then we know that the minimum number of edges is always going to be equal to n minus 1. In other words, our minimum number of edges is 8 minus 1, which is 7. Now in this particular graph, we actually had 8 edges. That means we had one extra edge on our graph, in which case our redundancy, as they calculated right here, would have been 1. Notice that the extra edge is really because it forms a circuit. Notice that B, G, and C, it forms a circuit. So again, we're looking at kind of these edges right in here. And if the redundancy is 1, meaning there's essentially only one extra edge, then there's really only one of these that we need to get rid of. We could either get rid of G to B, we could get rid of B to C, or we could get rid of G to C. By getting rid of any of those, we'll have a spanning tree. And so really there's 3 different ways. Again, here those are. So if you got rid of B to C, here's what it would look like. If you got rid of G to C, here's what that would look like. And if you got rid of G to B, here's what that would look like. So now let's take a look at another example of this. So in this next example, network has m equals 9 edges and n equals 9 vertices. Now remember, for our minimum number of edges, the formula that we can use is to take n minus 1. Now, that means that if there were 8 vertices, then 8 minus 1 is 7. Our minimum number of edges is 7. However, it has 9. That means that there were 2 extra edges that we don't need. In fact, now there are a couple of different circuits to look at. We're now going to have to, in order to find a spanning tree, discard 2 edges. But we want to make sure that they're not bridges. Because notice that A to B, so right here to here, as well as A to H are both bridges. If we were to get rid of those, our graph would be disconnected and it would no longer be a network and would no longer have a spanning tree. So bridges we have to keep. And so what we want to look for is our circuits. In fact, there are 2 circuits that we have. One connects B, G, and C. The other connects C, D, E, and F. So looking at those, there is a circuit of length 3, which again is this one right here, and then a circuit of length 4, which is this one right here. So we need to remove basically one edge from this. So from our 3, we're going to take away one edge. And then from our 4, we're also going to take away one edge, because remember our redundancy was 2. So we're going to take away one edge from each of our circuits, and then we should have our redundancy be 0, which means that our graph is a network and a spanning tree. Now, because there's 3 that we could take away here and 4 that we could take away here, that means that there are 3 multiplied by 4 is 12 possible spanning trees that we could have. In fact, that's what it's going to talk to us about on the next couple of slides. So if we were to get rid of BC and get rid of ED, that would again be taking rid of 2 edges. Now, with getting rid of those, our redundancy is now going to be 0. And when our redundancy of 0, that means that we now have a spanning tree. We could have also done it this way. So again, this would have been getting rid of GC and CD. That again gets our redundancy down to 0, and we have another spanning tree. If you wanted to know the total number of spanning trees, remember there were 3 different edges you could remove here, 4 different edges you could remove from this circuit, and that tells you that there are 3 multiplied by 4 is 12 different ways that we could choose an edge from our 2 circuits in order to create a spanning tree. So again, 12 different spanning trees that we could have done. So let's do another example of that. Let's take a look at some practice with counting the number of spanning trees. In this particular graph, we've got a total of 3 bridges. We've got H to A is one bridge. We've got A to B is a second bridge, and F to E is a third bridge. Those 3 edges, which I will go ahead and color in for us, are ones that we cannot remove, because if we were to get rid of any of these 3 edges, we would no longer have a connected graph. What that tells us is that we have a couple of circuits that we need to deal with. In fact, we've got one circuit here and a second circuit here. Now, determining which pair of edges that we can exclude is a little bit more complicated in this case. Notice that again it has 8 vertices. That means that 8 minus 1 tells you we should only have 7 as our minimum number of edges. And if our number of edges is 9, then we still need to remove 2. So again, our redundancy is how many we need to remove in order to have redundancy. There we go. So we still need to remove 2 of those in order to have it be a spanning tree. Let's go ahead and look at some minimum spanning trees. So this is going to kind of build on the example that we introduced back in section 7.1. We looked at, I think we called it a computer lab and the Ethernet connections between those. So notice we've got now some weights on our graph. And what we would want to do, remember there were multiple different ways that we could remove edges, but if we want a minimum spanning tree, we want to do so at a minimum total cost. And so if we want to do that, and again, remember these represented our computer labs where the edges are our different Ethernet connections, let's assume the weights cost $1,000 for each of the numbers. So in other words, this 90 between E and K represents $90,000 connecting those 2 computer labs with Ethernet connections. So what we would want to do looking at this is we want to look at our 2 circuits, because obviously if it's a bridge like from A to B, we have to keep this one in there. Same with G to H would need to be still there. E to K is also a bridge, so we need to keep that one. D to F is a bridge already, so we have to keep that. And J to L is also a bridge, so we need to keep that. Now, we also need to kind of think about how we can keep everything connected, but removing an edge so that we don't have circuits. Let's maybe take a look at this circuit on the left side first. Really, all we can do is remove one of these 4 edges right here. And when we do that, we're going to want to remove the one with the highest cost, meaning let's get rid of CD. And if we do that, our graph is still connected. C is now connected via B, and E still connects B and D, so we now have a little bit less redundancy for our network. Let's do the same thing over here on the right-hand side. Notice that we have, this time, 5 different connections. We should really only have 3, though, just like we did on the left side. So what we'll do is we'll remove the 2, which are the highest cost, 85 and 80. That would keep K connected to H, connected to I, to J, and would be at a minimum cost. In fact, that's what it'll talk to you about on the next couple of slides. But that's the idea behind what we want to do when we're creating a minimum spanning tree, is to get rid of those extra edges, those redundant edges, which cost the most. All right. So that's about it for 7.2. Hopefully that gives you a little bit better idea of what's called redundancy, as well as the main ideas behind minimum spanning trees being that they would have a redundancy of 0 and at a minimum cost, meaning get rid of the extra edges at a cheapest cost possible. That being said, until next time, have a great rest of your day.